Welcome to Finite Math, Chapter 3, Section 1, Day 1. So today we are looking at reciprocal, quotient, and Pythagorean properties for our trigonometric functions. So we have three reciprocal properties where the secant equals 1 divided by the cosecant equals 1 over the sine, and the cotangent equals 1 over the tangent. That means that whenever you multiply any trig function by its reciprocal, you should get 1, because 1 over tangent times tangent over 1 should equal 1. Now, a lot of this is based on some of our ideas from the unit circle or from trigonometry, where you have 3 portions to a triangle. You have the horizontal portion, which is oftentimes the x value. You have the vertical portion, which is oftentimes the y value. And the hypotenuse is oftentimes the r value. Now, last semester, we looked at how the sine of a function, the sine of an angle, is y over r. The cosine of an angle equals the x over r. And then the tangent of an angle is the y over x, opposite over adjacent. We also looked in the past at how the cosecant of an angle is the reciprocal of sine, so cosecant is r over y. The secant of our angle can be r over x, and the cotangent of our angle could be x over y. So with that information, we can prove a couple of things. So for example, we need to prove that the sine of x times the cosecant of x equals 1. Well, the sine of x, again, we could write as y over r, and the cosecant of x we can write as r over y, and all of that is supposed to equal 1. So if we simplify and multiply a little bit, y times r, let's keep that in alphabetical order and make that ry over r times y is already in alphabetical order, ry. And now we have a number over itself equals 1. So that means that this is an identity, that this number does actually equal itself. We could go through the proving process with secant, cosecant, and cotangent as well. We basically just proved this middle rule here, but the process for proving the other ones is going to be very similar. The quotient properties come from sine and cosine being able to be translated into tangent or cotangent, and actually, because of how secant and cosecant work, both of those can be translated into tangents as well. Now, part of this whole process that we're doing right now is called trigonometric proofs. We are using proofs right now, a little bit like in geometry. We're showing that these rules work before we're actually allowed to work with these rules. But we need to prove that tangent equals sine over cosine. Now, with trig function identities, with trig proofs, we're really only allowed to change one side of the equation, and usually we're going to try to change the more complicated side. Sometimes you'll be directed about which side of the equation you're allowed to change. But I'm going to start with the tangent of x equals the sine of x over the cosine of x. But sine over cosine technically is division. I'm also going to change my x's into thetas for a second because I would like to use x and y as the sine and cosine fractions like we have down at the bottom here. So the tangent of an angle equals the sine of that angle divided by the cosine of the same angle. But if sine can be represented as y over r, and cosine can be represented as x over r, then when we divide our fractions, we can keep the first one, y over r, change the division into multiplication, and flip to get the reciprocal of our the number that we're dividing by, the fraction that we're dividing by. And now we can cancel out a little bit. Y over r times r over x. I see an r that I'm multiplying by and an r that I'm dividing by. So now, let's put my tangent back in there. We have turned that sine divided by cosine into tangent equals y over x, which is actually already one of the formulas that we have, one of the rules that we have. So the sine over cosine was able to turn into something that became a tangent. Again, similarly, we can do the same thing with secant and cosecant values, but since those are the reciprocals of sine and cosine, it looks like the fraction got flipped a little bit. But the tangent of our angle is going to equal the secant of our angle divided by the cosecant of our angle. Again, the secant we could write as r over x, and the cosecant we can write as r over y. Again, keep, change, flip. So r over x times y over r. And again, the r that we're multiplying by at the top can cancel the r that we're dividing by at the bottom, and now we just multiply across the top. 1 times y over x times 1 becomes again y over x, which is again the same thing as tangent. So we've just proven and shown that the secant divided by cosecant can be turned into something that represents a tangent. Same way that the sine divided by cosine can be turned into something that represents a tangent as well. We also have some Pythagorean properties, which are all based on the Pythagorean theorem. Again, the Pythagorean theorem says that the lengths of any two legs squared, the sum of the squared lengths of any two legs of a right triangle should equal the hypotenuse squared. So we're kind of looking at the idea of u squared plus v squared should equal r squared. So we need to prove that cosine squared plus sine squared equals 1. Well, cosine, according to the variables that we're given here, is going to be adjacent over hypotenuse. So we can call that u over r squared. And then the sine is going to be the opposite over the hypotenuse, or v over r squared. And that should equal 1. Remember, when you have exponents over fractions, both the numerator and the denominator get the exponent. So we're really talking about u squared over r squared plus v squared over r squared equals 1. We can add fractions with like denominators, with common denominators, by just adding the top. U squared plus v squared over r squared equals 1. And now I'm going to break the rule that I just said, where we should only change one side of the equation. I'm going to multiply both sides of this equation by r squared for a moment so that we can cancel on the left. And hey, look, we just recreated the whole Pythagorean theorem based on cosine squared plus sine squared. So now u squared plus v squared equals r squared, which is the Pythagorean theorem, which we have already proven in geometry. So our Pythagorean properties, we actually have 3 rules that can be presented in 9 different ways. The major one is the one that we just proved, where cosine squared plus sine squared equals 1. But if you subtract the cosine squared from both sides, you can get sine squared equals 1 minus cosine squared. Or you can subtract the sine squared and get the cosine squared equals 1 minus sine squared. Tangent and secant are also related in a Pythagorean way. 1 plus the tangent squared will equal the secant squared. The secant ends up acting a little bit more like the hypotenuse in this case. And again, you can subtract tangent squared from both sides to get secant squared minus tangent squared equals 1. Or you can try to isolate the tangent by subtracting 1 from both sides and get the tangent squared equals secant squared minus 1. And we have the same relationship between cotangent and cosecant. Cotangent squared plus 1 equals cosecant squared. And again, we can subtract the cotangent squared from both sides to get cosecant squared minus cotangent squared equals 1. Or we can subtract the 1 from both sides to get that cotangent squared equals cosecant squared minus 1. So next, we need to prove the other rules. 1 plus the tangent squared equals the secant squared. So I'm going to look back at my right triangle here. Tangent is opposite over adjacent, so v over u. So 1 plus v over u squared is going to equal secant. Secant is the reciprocal of cosine, so secant is hypotenuse over adjacent, r over u squared. Again, because of how exponents work across parentheses, I can now turn this into 1 plus v squared over u squared equals r squared over u squared. I can multiply absolutely everything in here by u squared on both sides of the equation. Remember, anything you do to one side, you have to do to both sides. When I distribute here, the 1 will become a u squared, and the u squared at the bottom is going to reduce. And over here on the right, the u squareds will cancel each other out. Sorry, I meant cancel out on the with the v squared. But now we get u squared plus v squared equals r squared, which again is our version of the Pythagorean theorem from this particular triangle. And since we haven't used any specific numbers, we've just used general relationships and variables, this should be true no matter what kind of right triangle we're looking at. Same thing with the cotangent squared. Plus 1 equals cosecant squared. Again, cotangent is the reciprocal of tangent, so it's adjacent over opposite. So the cotangent is actually u over v squared plus 1 should equal the cosecant squared, which is hypotenuse over opposite, r over v squared. Again, we can turn that into u squared over v squared plus 1 equals r squared over v squared. And again, when we multiply both sides of this equation by v squared, we cancel the v squareds with the r. Distributing will cancel the v squared underneath the u, and it'll turn the 1 into a v squared. And once again, u squared plus v squared equals r squared is the Pythagorean theorem, so this must actually work for any value. So, for example, turn the expression on the left into the one on the right. This goes back to what I was saying previously about how we generally only want to change one side of the equation whenever we have these Pythagorean proofs. But we can take sine times cotangent and turn it into cosine. So the sine of x times the cotangent of x. Well, the cotangent of x, because of those reciprocal identities that we have, cotangent could be the adjacent over the hypotenuse, or it could be cosine over sine. So let's make this into the sine of x times the cosine of x over the sine of x. And again, since this sine of x is technically over 1, that means here I'm multiplying by a sine, and here I'm dividing by a sine. So those two cancel each other out, and they just give me my cosine of x. Example B, we need to turn the sine times the secant times the cotangent into 1. So the sine of x I'm going to keep as the sine of x, and I might even put it over 1 since both secant and cotangent have those reciprocal, they have those proportional, reciprocal, fraction identities. Secant is 1 over the cosine And cotangent is still cosine over sine. So it looks like we're multiplying by a sine at the top and dividing by a sine at the bottom, so those should cancel each other out. We're also multiplying by a cosine at the top and dividing by a cosine at the bottom, so those should also cancel each other out. And now this basically says, what is 1 times 1 times 1 divided by 1 times 1 times 1? That's a lot of 1.